Have you ever wondered how the AI in a game of tic tac toe keeps beating you? Me neither. But when you start thinking about it, it turns out to be a really interesting question. They often do so through a machine learning paradigm called reinforcement learning. In this video, we will explore Q-learning, what it is, and how it relates to reinforcement learning. Then we will apply our knowledge by creating our very own opponent in tic tac toe that adapts to our playstyle. Before we dive right into building our program, we must first understand some terminology. How do we give ourselves the best chance of winning in our game? Well, first, we analyze the state, the current observation of the board in a given instance. Then we assess what action we can take to put ourselves in the best possible position to win. Now, that's simple enough, but how exactly do we decide what the best action in a given state is? Consider this scenario. You're driving home and you're given the option of two routes. You could follow the left path and continue on the main road with traffic, or you could take the right path, a dimly lit road that stretches longer than the main road and has these weird but cute monkeys, but doesn't have as much traffic. In this case, the state is our current position in time. The actions are either going left or right. The reward, which is a signal we receive measuring our success, is inversely proportional to the amount of time it takes you to reach home. The faster we get home, the higher the reward. After you take an action, we observe the outcome, which becomes our current state. Analogous to our situation, let's say that we took the left path because we figured since it was shorter that it would be faster. Then the next time we were driving back and we ended up in the same state with the same available actions, we actually took the right path. It ended up that we saved more time taking the right path due to less traffic. Now, after repeated drives, we notice that this is actually a pattern that it's faster to take the right path than it is the left path. This introduces the concept of value, the long-term reward for being in a specific state. To refortify our knowledge, let's recap. Even though we might first assume that our reward would be higher if we take the left path, we observed over multiple drives, also we can call them episodes, that's a technical term for it, that taking the right path avoids unpredictable traffic most of the time and gets us home faster. Thus, the value of the right path, the prolonged reward, is larger since this maximizes the long-term reward. To put it simply, even though on occasion the left path may not have as much traffic, which leads to us getting home faster, it isn't as consistent as the right path over multiple trips. Here's a quick recap of how I define these concepts in a way that's understandable to me. An agent, a fancy term for the AI or the program that's making decisions. State, the current observation of the environment, which represents the situation the agent is in. Action, the choices or moves that the agent can make based on the current state. Reward, a signal that provides feedback on the success of an action or state, guiding the agent's learning. Value, the expected long-term reward for an action or state considering future outcomes. I know it might be getting tiresome, but we only have a few more terms to cover. The first of which is episode, a single training cycle where the agent starts in an initial state, takes actions, transitions through states, and ends in a terminal state. This is similar to how in the driving scenario we would consider our entire trip as one episode. Terminal state, the final stage of an episode, often associated with a reward that reflects the outcome, e.g. winning or losing. This is similar to reaching home. Non-terminal state, any intermediary state that occurs before reaching the terminal state. This is similar to the state prior to the one where we reached home. Policy, the strategy that the agent uses to decide which action to take in a specific state, based on its learning or predefined rules. For an example policy, we may pick a random path and calculate its value. After taking the strategy for a couple of episodes during the start, we gain more experience. We may then converge on an optimal policy by picking the best path most of the time and sometimes exploring to see if there's a better, more optimal path to take. This is what we refer to as exploitation exploration, where exploitation is taking the best known action in a given state and exploration is taking a random action in a given state. Now that we understand the different elements and terms involved within our problem, let's take a look at an application of it. Here's the Bellman Equation, an approach to solving for the value of state S under policy pi. Don't be intimidated by the symbols and jargon. It's actually very simple in practice. In fact, let's try to break it down into 3 simple parts. The first part is the probability of each action being selected under policy pi for all actions. All this part is saying is just, hey, in this state, what are the probabilities for all the actions we're able to take? The next part is the probability of a state and an action resulting in a specific new state with a specific reward. So this part is saying, when we are in this state and take this action, where do we land and how much of a reward do we get? The last part is a subsequent reward added with the discount factor multiplied by the value of the next state discounted by a factor gamma. This part is saying what is our total reward for considering the immediate reward we get and the value of the subsequent state. We consider the value of the subsequent state since we are not only considering the immediate reward we get, but where is this action or state put us in the long run. While the Bellman equation is more so used as a theoretical framework to set the basis for reinforcement learning and dynamic programming, let's try to put this into practice by revisiting our driving scenario with the two paths. Doing so will further reinforce the concept of how current state values are tied to the future state values. Consider these starting parameters. State S is a starting position. From state S, we can do either action 1, which takes the left path, or action 2, which takes the right path. From action 1, we can end up in state 1, which is light traffic and happens 50% of the time, or state 2, which is heavy traffic and happens the other 50% of the time. From action 2, we can end up in state 3, which is a smooth road and happens 90% of the time, or state 4, which is an unexpected delay and happens 10% of the time. Our policy is probabilistic, with action 1 being taken 50% of the time and action 2 being taken the other 50% of the time. Our rewards for each state transition are as listed, and our values for each subsequent state is initialized to 0, as we don't know their values yet. It is also worthwhile to note we represent the rewards as negatives since it is representative of the travel time, so the less travel time, the higher the reward. With this information, we can calculate the contribution for action 1 and weight it by the policy to get the contribution negative 8.75. Do the same for action 2, and we get the contribution negative 7.75. After we attain the weighted contributions, we can simply add them to get our final value of state S, which is negative 16.5. So now you might be thinking, this is cool, but where is the learning actually happening? This is where we would introduce a policy adjustment. Since we observed that action 2 had a more favorable contribution of negative 7.75 than action 1, which had a contribution of negative 8.75, we could potentially orient the policy so that instead of the actions having a 50-50 chance of getting picked, we bias towards the one that leads to a greater contribution. This would lead us in exploiting our best known action in a given state most of the time, and occasionally exploring a random state to see if we had potentially missed out on a different outcome. As a matter of fact, if we know the transition probabilities and our policy dynamics of every state in action, we can actually calculate all possible state values ahead of time. This would work in a maze scenario where we know exactly how the environment will respond to us doing a specific action in a specific state. I built this maze solver using Bellman optimality, a derivation of the Bellman equation that gets rid of the need for a predetermined policy and defines the value of a state based on the maximum value of the subsequent states for all committable actions. We can then derive a policy that takes the best action, which we define as an action that maximizes the subsequent state value. This is called a greedy policy, where we knowingly select the best action at every given state. I can make a separate video on Bellman optimality and its applications if that is something that interests people, so please let me know. So this is really cool. We have found out a way to calculate all state values and then derive an optimal policy from there. However, what happens when we don't know the state transition probabilities? For example, how would we tackle our driving problem if we didn't know what percentage of the time we would get heavy traffic or light traffic? The only option we would have is to take multiple trips and deduce from experience. Luckily for us, there's an algorithm that does just that. Q-learning is an off-policy reinforcement learning algorithm that can be used to derive an optimal policy without knowing state transition probabilities ahead of time. Here's the formula for Q-learning. And much like we did with the Bellman equation, let's break it down into 3 easy parts. The first part is the current value of the specific state with a specific action. The second part is the reward for the state transition added with the max value of a specific action in the subsequent state discounted by a factor of gamma, which is also referred to as the discount factor. The last part is subtracting the current state action value from the new estimate in order to better our estimate. This is called the temporal difference error and the heart of our update rule. This is basically saying how far off was our current estimate of the state action value with the new estimate. Putting it all together, we can refer to this diagram to get a full picture of Q-learning. We can then use Q-learning to formulate this full algorithm in order to deduce the optimal policy in a given problem, such as the one in our Tic Tac Toe game. Here's the diagram. So let's address each of these elements one by one, starting with our step size. From this point on, we will refer to it as learning rate, and we will set it to 0.3 as a default. It functions exactly as it sounds. The higher the learning rate, the faster it will learn. You might be wondering, why not just make it learn as fast as possible to speed up the process? Similar to how you and I learn, if we are shown multiple ways to react to a certain scenario and we place too much emphasis on our most recent experience, we will likely forget our past experiences. This leads to imbalance and inefficiency because we're essentially operating with only our short-term memory. Analogous to our situation, if the agent learns too fast, i.e., places too much emphasis on new information, it won't find a way to strike a good balance between its past experiences and the new information. This is because too high of a scalar value will make it so that it treats the newest information as the most important, therefore it will overadjust. Epsilon, which we will set to 1.0 so that it always explores initially. For initializing our Q table, we need to store a state, its allowed actions, and the value of each action within the specific state. To represent this within Python, we will use a dictionary that accepts tuples of tuples as a key to represent the state, which will have a corresponding dictionary of actions and their values. Let's talk about our training loop, as this is where the actual learning occurs. Our first step is to initialize S. Store 0.0 for all values of actions that have not been committed yet. This is necessary since if we're going to be taking the max value of all actions in the state, we cannot have undefined values for said actions. Then we select an action depending on the epsilon greedy policy. After that, we observe the resulting Tic Tac Toe board and its rewards. Then, perform a Q learning update. So this is where we actually update our Q table and see what we learned from the resulting state. We then repeat until it hits a terminal state. So that would be either a win, lose, or a stalemate. Then we reduce epsilon by a small percentage. This will mark the end of one episode, which we will repeat for a large number of episodes to ensure we cover multiple state action values. Unfortunately, due to my poor editing and narration skills, I will not be live coding and commentating. However, I will provide screenshots of each section and explain what it's doing. This part of the video is not meant to be a tutorial on PyGame or tkinter or any of the other libraries we use, but rather an educational implementation of Q-learning in the context of Tic Tac Toe. To make things easier for us, we will use a pre-existing implementation of Tic Tac Toe in a PyGame from a creator named Barto. I highly recommend checking him out if you want to understand the PyGame aspect of our program. His video will be linked below. Now we can get into the code. We will go from top to bottom in sections and I will commentate on each section for our understanding. First, we will have the following imports. OS to set the flag to 1 to stop PyGame from printing its welcome message to the terminal. PyGame to build our Tic Tac Toe game and sys to exit the program when PyGame terminates. TQDM will give us a loading bar in the terminal so we know our progress in the training loop. Default dict, which will help us with the dictionary that instantiates a key automatically without having to instantiate it prior to an operation. Matplotlib's pyplot will help us visualize our agent's progress. Tkinter to get simple dialog boxes that will get user input. Then we need to instantiate some variables. We will use 3 boards. One for our actual board, which will hold the O's and X's. Another will be our graphical board, and lastly we'll have our logical board, which copies our actual board, but uses 1 to represent X and 2 to represent O, and 0 to represent empty space. This is basically so that we don't have interference between both boards. Now let's get into helper methods. This function renders our game within a window. We'll use this function to add an X in our gaming loop. All it does is place an X in our board and a 1 in our logical board. It then renders it on the window. We'll use these functions to place an X or O depending on which one we call. This places it on the board and places it on the logical board as well. This function determines the winner of a game. It first checks columns and rows, then diagonals. If it doesn't find a winner, it returns a draw message. This function is the same, but this actually updates the graphical interface. We separate these because we do not want to see the graphics during our training loop, as this would be computationally expensive and time consuming. However, we do use this function when it is our time to play the game. We can get a list of empty spots in a given state using this function. We use these as helpers to see what our agent is actually learning. The first function is to see our entire Q table. We use this so that it's not entirely a black box algorithm. Rather, we can look into it and understand what our agent is learning. The fun part about this is that we can see how our agent learns after each episode, and we will analyze it later to see just that. The second function will only print the given state from a given Q table and its corresponding actions and their values. Here are the examples of the functions in their respective order. This function simply opens a tkinter window to ask the user for 3 things. The max episodes we want to run, which we initialize to 20,000 as a default if input is not given. The learning rate, which we initialize to 1.0 so that it always explores at the start. The discount factor, which we initialize to 0.3. This creates a tkinter choice window that lets the player decide if we want to go first or second. Due to the way the code is set up, we will always play as X, but this choice just decides if we are playing the first move or if the agent is playing the first move. We need to set up some variables to get all the required information before we set up the training loop. We first set up count to track how many games/episodes we have actually played. We then set up win-loss and stalemate count to track the result of the games. We also set up our Q table as we mentioned before. Then we set up 2 arrays to track our statistics over multiple episodes so that we can later display them using a pyplot. After that, we get the player choice and their selected learning rate, discount factor, and number of episodes. Finally, we initialize the loading bar so that we can see our training progress within the terminal. Now we can get to the training loop. I know the code might seem a little complicated, and to be completely honest, it kinda is. But let's go at it piece by piece to understand it. First, we will maintain a game finish flag so that if it is true and the game has concluded, we can reset all the boards to start anew. For this training loop, we will be training against an opponent that selects positions at random. Now you might be thinking, why would we just pre-train it instead of just playing against it? It would be more accurate to our own playstyle. Well, firstly, most of us don't want to play 10,000 games of Tic Tac Toe so that our agent is specifically tailored to play against us. We also pre-populate the Q table by playing against a random opponent because it is easy to implement and we lack a full model of the environment. A model in the context of reinforcement learning is basically having a complete understanding of how the environment will respond to a specific action. For example, in a fully modeled Tic Tac Toe environment, if the agent places an O in the top right, it would know the probability of all the responses the environment would give. By playing it against a random opponent prior to playing against us, we can achieve a better than random chance of the agent winning against us while requiring far less extensive human input and effort. Let's analyze the first if statement. All this is doing is that if it's currently X's move, plays an X randomly on the board and switches to O's turn. The else statement is basically what happens when it is O's turn. First, we save the state prior to taking the action as a tuple of tuples under the variable's last state. We then initialize all the state action values for the last state as 0 if they have not been previously initialized. This ensures that we don't overwrite values and only set values as 0 if they have not been encountered yet. After that, we select our action depending on the current value of epsilon. We basically say that if there is an epsilon% chance, it will randomly choose an action, which is our exploration, and then there's a 1 minus epsilon% chance we choose the best known action, which is our exploitation. After we take our action, we get the new state and the actions we can take in the new state. We also want to encourage the agent finishing the game reasonably fast, so we assign a negative reward of 0.005 for non-terminal states. We also have a catch, so that if we don't have any actions to take because the board is full, we can only have a max value of 0. You may be wondering why we wouldn't just immediately check for a winner or stalemate if the board is full, and the answer is, I'm kinda lazy. We do end up checking for terminal conditions, but only after we get the max value. This if statement becomes necessary when no actions are available because O is the last move before reaching a terminal state. Without it, attempting to retrieve a maximum value from an empty set of actions would result in an error, which is why the check is in place. You could potentially circumvent this by checking if the board is full after each action and right before the new state is evaluated, but this is functionally the same thing. Then we want to perform an update in the non-terminal state. Here's the side-by-side of our code and its adherence to the formula. As you can see, our code directly matches the Q-learning formula, ensuring we're doing a proper update. This brings us to our win conditions. If we find that the board has hit a terminal state, which we check immediately after X has been placed or immediately after O has been placed, and we evaluate the new state, we want to perform a terminal Q update. We also assign a reward of +1 if the agent wins, -1 if the agent loses, and 0 if it is a stalemate, and we also update our counts respectively. Due to no actions being available in terminal state since we have filled up the table or someone has won, we will disregard the value of the terminal state in the context of Q learning. Therefore, our equation will look like this, and our code will reflect accordingly. After we have performed the terminal Q update, we will reset the board by making the game finish flag true. Then we will lessen the epsilon greedy policy by just a little bit to encourage more exploitation since we have learned to be slightly more optimal each passing episode. We then increase count since the episode is concluded and then update the progress bar to reflect such as well. This concludes our training loop, so congrats, the hard part is over. Now let's close the progress bar and move on to showing the results of the training loop. We can do so using this code. For example, on this run of 20,000 episodes with default values against a random opponent, our agent landed a win rate of 38%. It is also worth noting that since our agent always went second, this win rate is far less than what we would have if our agent went first, since Tic Tac Toe is biased towards whoever goes first. In a few other runs, if our agent goes first, we observe a win rate of near 77%. After that, we reset some counters and initiate the PyGame window and update the display to reflect as such. Now here's the rest of the code in its entirety. For ease of understanding, we will break this down part by part. The entire body of the code will be run in a while true loop so that it runs indefinitely till the user closes out the window. To capture a window close, we use a PyGame event listener. Upon close, we print some statistics in a similar manner to how we have done before, but this time we also show a pie plot of the win rate over our played games. I won't spend too much time on the actual game loop, as it's very similar to our training loop, with the difference being we actually play against our agent this time. We have an event listener for every time we press the mouse button down, which lets us place down X. We also use it to trigger our agent into placing an O. So now you might be wondering, why not just immediately place an O down after we place an X to save the mouse clicking? And the reason is, it requires work, so I didn't do it. But we can move on to the agent's logic, and thankfully, it is exactly the same as the training loop's logic, so we have already covered it. Lastly, we have this bit of code that serves as a game stats checker and outputs a terminal every 3 games. And with that, we've successfully completed our program. We've trained and played against our very own reinforcement learning AI, capable of adapting to our playstyle. Now let's take a look at the Q table to see if it's actually performing as expected. By analyzing this, we can gain an insight into our agent progressively learning and adapting to our playstyle. For demonstration purposes, I was playing the same move over and over again to see if it would respond to the strategy. My strategy was to try to get a row win using the middle row, and as you can see by the increasing value for the moves the agent took, it learned to exploit the top row when I employed such a strategy, and reflected this in its state action values by increasing it. We can leave our program here, but let's think of ways to potentially make our agent smarter. We know that humans don't largely play at random, so how do we simulate a more realistic opponent strategy to play against our agent? Well, we know we can't create a model of ourselves to play against the agent, as it would be tedious and nearly impossible to calculate all our possible responses to every action that the agent might take. But here's a better idea. Let the agent play against itself. By employing the concept of self-play, we can train our agent against an opponent that learns and adapts to the agent. This is more representative of how you or I might play, basically iteratively learning each other's moves in order to win. Luckily for us, this is very easy to implement in our pre-existing code. We just have to tweak the training loop. First, we can basically copy and paste the agent's logic in the else block to our if block for when it's X's turn. I readjusted the variable names to ensure there is no overlap or overwriting, but I think it's optional. I made it so that non-terminal states get no reward, but you can experiment to find out what is most optimal. We then have to adjust the winning conditions to ensure that the agent's opponent is also getting a terminal update. It's pretty much the same, with only the reward differing, since if O wins, X must lose, and etc. This sums up all the changes we must make to change our opponent behavior from random to self-play. This concludes my most up-to-date iteration of the program, and I hope you enjoyed it. This was a passion project of mine, so my winter break wouldn't go completely to waste, but I'm trying to learn more about reinforcement learning as I have this project in mind, which I can hopefully unveil in the near future. If I have made any errors, or if you all have any suggestions, please comment and I'll be sure to make a pinned comment of all the errors to correct. This project is also in my GitHub, which I have linked in the description, and thank you so much for watching and sticking to the end.